everything we've done so far is as far as derivatives go, is the only application we've used is rate of change and slope. And there are a lot of other applications of derivatives, so that's kind of the idea of what we're getting into here. The first thing we're going to talk about is something called extreme values. What does the word extreme mean? Yeah, it's like as far as you can go, right? So when we're talking about extreme values, what we're really talking about are maximum values and minimum values. So what is the biggest the function gets? What is the smallest that a function gets? And we'll be talking about these from two different perspectives. From a global or an absolute perspective, for an entire function, for all of its defined values, what is the greatest value that it takes on and the lowest value that it takes on. But we're also going to look at it from a local perspective, from just a small area of the graph, and see what are the largest values and the smallest values within a particular region. So let's get into it here. So the first thing we're going to talk about is something called absolute extrema or global extrema. Extrema is the plural of extremum. Extremum is a Latin word that means extreme. And so when we're talking about extrema, we're talking about maximum values and minimum values. Let me write that down here. So we're talking about the maximum value that a function takes on, or a minimum value. So we'll kind of generalize maximums and minimums and clump them all into this group that we'll call extrema. Maximums and minimums are actually very, very closely related. We use the same process to find maximums as we do minimums. What's the difference?
One's big, one's small.
Well, yeah, one's the biggest value, one's the smallest value. So if we were to take a graph and just flip it over across the x-axis, our maximums become minimums. So we use the same process to find maximums and minimums. It's a reflection across the x-axis, essentially, for what we're doing to find one or the other. So what does it mean to be an absolute extrema, an absolute maximum, or an absolute minimum? What do you think? So let's say we've got this function right here, and I ask the question, what is the absolute maximum value of that function? What are we looking for in terms of this picture here? Cole? The highest point, right? Would it be valid to say that this is going to be our absolute maximum? No. Why would I pick this point here? Okay, it is actually going to be what we call a local maximum, or a relative maximum, but it's not an absolute. So this point right here has some properties that are interesting, and it is going to be a type of maximum, but it's not the absolute maximum. This one is. Now, in a lot of respects, these two have exactly the same properties. But, and we'll get to some of those later, why is this one the absolute maximum?
That's the highest it ever goes.
It's the highest it ever goes. So this y value here, whatever it is, that's the highest value that the function takes on. So let's say that this right here is c, then this value right here would be f of c, and so the absolute maximum would be what? C comma f of c. So this would be the absolute maximum. Does that make sense? That's pretty intuitive, I think. Don't you think? Yes.
Why can't you just put f of c, since that's the best of value?
It depends on how the question's asked. Usually we're looking for a point and not just the value. So we use the value to figure out what it is, but then we have to write it as a point. Sometimes it may say what is the absolute maximum value of the function, and then you would just say the f of c part of it. Okay, good question. Okay, does this function that I have drawn here have an absolute minimum? No, it does not. Why not? Yeah, it goes on forever as it goes down here. So it's going to go to negative infinity. In fact, it's going to go to negative infinity as x goes to the left and as x goes to the right. So it does not have an absolute minimum. So it's possible for a function to have an absolute maximum or an absolute minimum. It's possible that it doesn't. Okay. Now, sometimes we talk about a function as a whole. Sometimes we'll be talking about a function on an interval. So if we wanted to look at a function on an interval, let's say we have a function that looks like this. We'll make it a closed interval to start. Let me ask this question first. Does this function have an absolute maximum? Does it have an absolute minimum? Yes. Somebody describe to me where the absolute maximum is. Which quadrant is it in? It's in the second quadrant, right about there. You guys agree? So that right there would be an absolute max. And this right here would be an absolute minimum. It's easy enough, right? Okay, what if we had a function that looks, let me back this up here. What if we had a function that looks like this? Oh, I'm going to use red. Does that function have an absolute maximum? Yes, right there, right? You guys agree with that? Does it have an absolute minimum? Yes, it does. Where is the absolute minimum? The right endpoint. So the right endpoint in this case is the absolute minimum. And this right here is the absolute maximum. Now let me ask this question. Is it possible to draw a function, a continuous function from the point at x equals a to the point at x equals b that does not have an absolute minimum and an absolute maximum? So is it possible to draw a continuous function from this point to this point that does not have an absolute minimum and an absolute maximum? Think about that for a sec. Is it possible to draw a continuous function from this point to this point that does not have a global or an absolute minimum or an absolute maximum? No, it's not possible. So this is actually something called the extreme value theorem that says that if you have a closed interval, if you have a continuous function on a closed interval, then that function has to have an absolute minimum and it has to have an absolute maximum, whichever was the other one from what I said. So it has to have an absolute minimum and an absolute maximum on a closed interval as long as it is a continuous function. Now, why does it have to be continuous? Why is that important that it's continuous? Let's come back to that. We'll talk about the extreme value theorem in a minute. The other type of extreme that we're going to talk about is called a relative extrema, a relative minimum, a relative maximum, or we could also call it a local minimum or local maximum. And they both have the same idea. And I'm going to put a picture up here that's pretty similar to a function that I put up here earlier. Where do you think this function has local extrema? So describe them to me. We did say that this point right here was an absolute maximum.
Don't we need some kind of domain?
We don't. No, I'm not worried about that. Okay, the one in the second quadrant. Would you say that this is a local extreme? Would that be a local minimum or maximum? Okay. Anything else? Right about there? What would that be? That would be a local minimum. How about this point right here? Would that be a local extreme also? Yes. So you guys seem to have a pretty good grasp of what the local extrema are. So what does it mean to be a local extreme?
It's an extreme. It's not the most extreme.
Okay, it is an extreme, but it's not the most extreme. At least not necessarily the most extreme. It could be. What else would you say, Willie?
I said just to be extreme in general. Unless it's going on forever.
Okay, I think I know what you mean by that. What do you think?
It's a point where the slope reaches zero.
Okay, that's a good observation here. At all of these extrema, the slope of the function is zero, which means that the derivative is going to be equal to zero. And that's actually the first time we've said anything about calculus, isn't it? So of all this talking we've done so far, that's the first calculus has come into play. And that's true. We'll come back to that. But what makes this a local maximum even though it's not the absolute or the global maximum?
It has the highest value of points around it.
Yes, that's exactly right. That's very well put. It has the highest value of all of the points around it. So within some region, within some interval, I'm on the wrong one here. Within some interval, and it doesn't matter how big the interval is, but within some interval around that point, it is the largest value in that interval. So the idea of a local extrema is it is the extreme value within some interval around it, in its neighborhood. Okay, that's why we call it local, because it's close to it. So we could have infinitely many local extrema. In fact, can somebody give me an example of a function that has infinitely many local maximums and infinitely many local minimums? Sine or cosine, right? In fact, every one of those are also global maximums. You could have more than one global maximum because they're all equal to 1, right? So they all have the same maximum value. All right? So the idea of a local or a relative minimum or maximum is it's an extreme within its own neighborhood. All right? And there's a way in calculus to formalize that. We don't need to be extremely formal about it as long as you understand what it means to be local, to be a local extreme. Okay, we good with this? I want to draw another graph on here real quick to kind of show. I've been graphing differentiable curves, and we could end up with something like this. Let me do that. If we had a function that looked like that, describe what's going on here. What would we call this point right here? What'd you say, Tilly?
Global max.
Okay, I agree. That is a global maximum. It would also be a local maximum. How about right here, this point? So we got this one. That's a global maximum and a local maximum. How about here? That's a local minimum right there. Okay, how about right here? Local maximum. Okay, do you see any other points there that might be a global or a local minimum or maximum? Okay, now I picked this point right here. Sorry, I picked this point right here because it had the property that Nate pointed out earlier. It has what? The slope of the tangent line is 0. So if I were to draw a tangent line to that point, the slope of that line would be 0. Okay, so it's easy to see why I picked that one out. Why did I pick this one? Is the slope of the tangent line here 0?
No.
Or this one? Is the slope of the tangent line here 0? What is it? It's undefined. So we saw in the last picture that I drew that we're going to get local minimums and maximums when the tangent line is going to be horizontal, when we have a slope of 0. But we're also going to get local minimums and maximums sometimes when the derivative is undefined. Exactly. So there's really two places that we want to look for extrema. We want to look for extrema when the derivative is 0. We want to look for extrema when the derivative is undefined. Do I need to look for derivatives? Do I need to look for extrema when the derivative is, say, like 1?
No,
Why not?
because it wouldn't be a max or minimum then.
Okay, let me use -1 here as an example, just so I can put it on the graph here. So why is it impossible to have an extreme value right here at this point?
Because there's something above it and below it.
Yeah. So when the slope here is -1, we can see that in the neighborhood of that point, if we were to zoom in on that point, there would be points close to it that are below it to the right and above it to the left, because the slope of that curve is -1 at that point. So if the slope isn't 0, it's not possible to be an extreme, because to the left and to the right we're going to have values that are greater and less than that point. Does that make sense? So the only places we have to look for extrema are when the slope is 0 and when the slope is undefined. Does that make sense? Okay, moving on. Critical points. Critical points are critical to extrema. That was really bad. So this is actually a formal idea in calculus. A critical point is any point on a function, and I'm going to write this out here because you need to know what it is. On a function, I'm going to name the function just so I can use it. So on a function f of x, where f prime of x is equal to what? What do you think? 0. Or f prime of x is undefined. So anywhere that the derivative is equal to 0, or anywhere that the derivative is undefined, we're going to call that a critical point. So these critical points are important to us because they are the only points on a function that can be we just said it, extrema. So these are the points here that are potential extrema, whether they're local extrema or global extrema. Now that might be a little bit misleading. This is true on a function that's defined for all real numbers, whose domain is all real numbers. If we restrict the domain to an interval, then we add a couple of options for extrema. So if we restrict our domain to an interval, what other points could also be extrema? The endpoints, exactly. So when we're looking at a function that's defined for all real numbers, then these are the only potential extrema. When we start looking at intervals, then the endpoints and the critical points are your potential extrema then. Does that make sense? Okay. So how can we tell if it's an extreme value? The important thing here with local extrema is that it must be a critical point. The extreme value theorem it's a pretty important theorem in calculus, or at least it uses calculus to prove the theorem, although it's not necessarily a calculus theorem. You don't use calculus in the theorem itself. And it's a theorem that's called an existence theorem. The extreme value theorem doesn't tell us how to find the extreme values, but it tells us when extreme values exist. So existence theorems are useful to tell us when something's going to happen, but it's not useful in telling us how to figure out where it's going to happen, if that makes sense. And I'll explain that more later as we do some examples. So the extreme value theorem says exactly what I said earlier. If if we have a function f of x that is, it's continuous on the closed interval a to b, then the function has an absolute or a global maximum on that function or on that interval. So this kind of gets at what you guys were telling me earlier. If we have a function with two endpoints and we try to draw a continuous function from one endpoint to the other, at some point we have to have a minimum and a maximum on that interval. Yes?
Okay, so, but if there's a function...
So if a function has two maximums, two local maximums that have the same value, then it would have two global maximums. So it would attain that global maximum value at two different points. So we would name both of them as global maximums, yes. And the same thing with minimums. When we're talking about extrema, if we say one thing for maximums, the same thing's going to be true for minimums. So I may leave one of them out, but it works for both. So the same idea as I said earlier. If we started a point, we ended another point, doesn't matter how we draw the function from one to another, we're going to get a global maximum and a global minimum at some point, even if it's a straight line. If it is a straight line, where are the extrema going to be? At the endpoints. Okay, now, I have two questions for you about this theorem. Why does it have to be a closed interval? Why couldn't it be something like this for this theorem? Why couldn't it be open intervals? Is that an issue with this one that I just drew? No. When would it be an issue? Okay, the straight line would be a good example here. If it's an open interval, then what is the absolute maximum? Where is the absolute maximum? It doesn't exist. And it's kind of a tricky thing. Let's say that we're on a coordinate plane here. And so really doesn't matter what this is. Let's say this is a value of 3 right here. Does the function ever attain 3 as a value? No. Does it attain 3 or 2.9? How about 2.99? How about 2.999? Yeah. So where do I stop? How about 2.9 repeating? Actually, no, it doesn't, because 2.9 repeating is equal to 3. What? It's crazy. It is. So we can add as many 9s as we want, as long as it's not infinitely many of them, and we can always get a number that's closer to 3 than where we are. And if you don't believe that, if you pick a number that's a little bit less than 3 and you think it's the biggest number that's less than 3, just average that number in 3 and you get a number that's bigger than that and less than 3 still. So it doesn't have an absolute maximum here because it has a ceiling. It can't go past 3, but we don't know what the biggest value is. And the same thing with the minimum. So that's why it cannot be, that's why it has to be a closed interval. It can't be an open interval. The other question is, why does it have to be a continuous function for this theorem to work? Why couldn't we have something like this? I think I made this one obvious. Cole?
Well, there's like no limit there.
It's true there's no limit. So remember what the extreme value theorem says. It says that in certain cases, the function has to have an absolute maximum and an absolute minimum. Does this have an absolute maximum and an absolute minimum?
No.
No, it has one. It has an absolute maximum, right? Does it have an absolute minimum? No. We get close to an absolute minimum here, but we can't say what value exactly it is because it's it's an open interval. So it can't be continuous because you could have all sorts of problems with a discontinuous function. You could have asymptotes involved. You could have stuff like this involved. You could have gaps where we don't have anything defined. So for the extreme value theorem to work, it has to be a continuous function. All right. Any questions about that? So again, the extreme value theorem is just a theorem that says in these specific conditions, when we have a continuous function that is on a closed interval, then we know that it has to have extreme values. Otherwise, we don't know that it has to have extreme values. We could have something like this. We could have an asymptote. If we had an asymptote here, then we could have, in this case, we would have an absolute minimum but not an absolute maximum. So we could have one without the other, or we could have neither. It would be possible if we had a function that looked like this, and there's your asymptote there. Okay, so then it doesn't have a maximum or a minimum. All right, any questions about any of that?